project. I'll allow these gentlemen to introduce themselves and their project.
Hello everyone, my name is Austin Cross.
My name is Joel Dewey.
Jevin Barnett.
I'm John Lynch.
And our project is the Sunseeker Maximum PowerPoint Tracker Array Controller. Start with some background. Sunseeker is a registered student organization that allows a team of students to build, design, and race a solar-powered vehicle. Every other year they compete in a race called the American Solar Car Challenge, which competes against other universities. For this project, Sunseeker had a need to create an array controller that would help them make it, they had to have an array controller that controlled their PowerPoint trackers to allow them to have an electric gas gauge, as said, by measuring a state of charge through current and the coolant counting, and we'll discuss this in upcoming slides. And the information from the array controller also had to be shared with other car electronics, and it plans to be implemented in the 2016 Sunseeker car.
This is the Sunseeker 2016 power distribution diagram. It consists of three critical power subsystems: the battery, which is on the bottom, as Joel pointed out, the array, which is what we control, on the top, and the motor controllers, which you can see on the right. The next generation battery protection system is in charge of controlling the flow of charge throughout the entire car, as well as monitoring the state of charge. And how it will communicate with our controller, which is the brains and controls the array, is by sending a message to our controller stating that the battery is low and needs charge. Then our array controller will turn on the maximum PowerPoint trackers and allow charge to flow into the battery.
This is the Sunseeker 2016 array electronics. As you can see on the top is the three sections of the solar array, which then take in energy from the sun, and then that maximum PowerPoint trackers optimize the charging of the array to the battery. And as you can see, our array controller, our project, is in the center, and it shares the same CAN bus as the MPPT, so we can communicate with it. It also has a shunt on the right side, as Joel's pointing out now, and that's where we conduct our coolant counting for a state of charge.
Part of our first semester or in senior design was to come up with a list of specifications that define our array controller. Some of these specifications include functionality, so that would be the driver switches to enable and disable the MPPTs, as well as the driver enable switch, which is what the driver switches to start the car. Mechanical considerations, so the gauge of wire, the size and dimensions of the connectors, and the size and dimensions of our enclosure for our box over there. Our hardware, so that includes having to pull from the 12-volt supply on the CAN bus using the isolated DC to DC converter, measuring the current shunt, measuring the different types of sensors, and using the MSP430 microcontroller. Our software included writing a main code routine implemented as a state machine, and then also having individual critical software components such as a car CAN bus, a MPPT CAN bus, ADC, RS-232, and our coolant counting algorithm.
The MPPT is John's pulling up right now, and it is utilized to maintain an efficient operating point to charge the batteries. And it's done by operating at that maximum power point where the power of the solar array is at its greatest. And this is used to ensure efficiency. And we also communicate with command and control via CAN messaging.
Coolant counting is one of the main operations of our array controller. Coolant counting is where we measure a voltage across this resistor here and convert that into a current in the software. By integrating that current with respect to time, we're able to figure out how many coulombs have entered the batteries, and with information from the 2B design battery protection system, we were able to figure out exactly what the state of charge is for the batteries, make an informed decision as to whether or not to have an MPPT on or off. We do smooth out this voltage reading by passing it through an infinite impulse response filter, which acts as a low-pass filter.
For the beginning of our PC board design, we had to start with circuit design elements, and we started off with some SPICE design, which can include our DC to DC converter, which included an isolated interface so we could define our own ground. And then we transition into our shunt design, which would actually be used to measure the shunt resistor that is done there for the cooling counting. And we also considered our NTC negative temperature coefficient thermistors.
And then we had to design our digital circuits, which consist of the RS-232, the controller area network circuit, and the analog to digital converter. All three of those were designed based on data sheets and application notes, also with prior knowledge of Sunseeker projects. The RS-232 is isolated, meaning that when the laptop is hooked up to the RS-232, they are on two different grounds, so if, just in case of surge currents, the laptop will not be harmed. The controller area network is also separated from the car through digital isolators, again, just in case surge currents from the car will not damage our board or the microcontroller. And then our analog to digital converter has 8 inputs, and they are self-checking diagnostics or sensor measurements.
This is our shunt design, and as you can see, U1 and U2 are op amps. And U1 is our buffered unity gain voltage ref, which will output a voltage of 1.25 and act as a offset to the diff amp. And the voltage reading from the shunt will be read in as VREF, as the non-inverting side of the op amp, which will then be passed through our diff amp of a gain of 14, and then the capacitors act as a low-pass filter to filter out high-frequency noise.
This is our preliminary power supply design, which, as you can see on the left, is the LT3575, which provides a one-to-one conversion from the 12 volts from the car, to our board. That output goes into a transformer for isolation, as Jevin said, because we wanted to define our own ground for purposes that we did not want to share the ground as the car, just in case if the car decided that our board was ground. We didn't want surge currents going there and destroying our board. The output of the transformer then feeds into the maximum power point trackers to power them, and it also feeds into 2 LTC 3621s, but we're only showing one there. But one of the LTC 3621s will provide 5 volts. We'll step down the voltage from 12 and provide 5 volts for our analog components and our RS-232 circuit. And then the other one will provide 3.3 volts to the rest of our digital circuits. We, however, through our design process, we found out that this TDK lambda part does the one-to-one conversion from the car 12 volts to our volt, or the 12 volts that we need, and also provides isolation. So we decided to use this part because it alleviated risk because we already knew it worked.
This is the array controller schematic block diagram of all the functional components inside the PC board. And at the center, you can see that we opted to use a Texas Instruments MSP 430. And then we also used our digital circuits, as John mentioned earlier, the RS-232 interface and the CAN MCP 2515 CAN controllers for the separate CAN buses. We also used a analog device 24-bit analog to digital converter. And as you can see, the shunt is a connector to the board via a microfit connector to the diff amp. And that's fed into our low-pass filter and diff amp to our ADC. And as you can see, we have a VREF, voltage ref, which is a self-checking that John talked about earlier, so we can check faults on ourselves. We have a self-diagnostic board.
Well, next we're talking about our printed circuit board development, which will include the schematic capture, the PCB layout, board fabrication, assembly, testing, and integration.
Every PC board, as I said before, has to start with schematics, and then after we've designed our schematics from data sheets, application notes, prior Sunseeker design, we have to implement them in the schematic capture functionality of PCB 123. The circuit on your left is a microcontroller circuit complete with a programming interface, reset switches, 6 LEDs, and off-page connector tabs. And the circuit on your right is our 2 CAN buses, one for MPPT CAN on the top, and then for the main bus CAN on the bottom. And each CAN circuit is powered up U10. You can see in the far right is our voltage regulated by Motorola.
Like Jevin said, we used PCB 123 to develop all of our schematics and the layout. And this is our initial layout design. And we had to think logically where we were going to place all of our mechanical components on the board. For example, we had to make sure we could put the analog components together, the digital, our power supply, and so on. This is our finished completion of the board layout. The picture on the top left shows all of our components that are logically placed and separated. Then we chose a 4-layer board, And our second layer, or the inner layer, as you see the purple, is our power layer, which is completely devoted to power. Below that is our ground layer, completely devoted to ground. And then the top and bottom layers were devoted to traces, and the top layer especially had all of our components on it. And whatever we didn't use, whatever space was left over, we filled with ground, with the ground fill-in, to make sure ground is ground. And then if you see the picture on the right, that is our part of our power supply, and those rectangular connections we decided to use because if we use single traces, there's a potential for breaks because of the current, the high amount of current. So if we use a rectangular polygon, we spread out the current to alleviate some risk.
After the layout and the schematic capture were complete, we sent off our designs to Sunstone Circuits, the manufacturer of our printed circuit boards, and we received back the pre-assembled board on your left. And after we received our parts from DigiKey, we placed them and soldered them on the right side of the board of the post assembly. So we received the pre-assembled boards on the left, and then we ended up with the finished product of the post assembly boards on the right.
After fabrication, we had to start integrating our software with our hardware, so we took an incremental testing approach. First, we made sure that the board was had all power to it and had the correct voltage levels. And then we could start testing the microcontroller to see if it's communicating with all of our devices and the clocks were working with it. And we used an oscilloscope to verify all of our signals were being sent out, had the correct voltages and also the correct frequencies. And we also started our software design, so we had a maintenance program that ran our state machine and also implemented our critical software components such as the ADC module, which read in all of our inputs, the CAN, controller area network, to the vehicle, which sent and received messages to other car electronics, the CAN MPPT, which was isolated, and it used a remote transmit request, or RTR for short, to retrieve information from the MPPTs concerning its voltage, temperatures, and currents, and also the RS-232 output, which would dump information into a PC for users to see.
After we completed the incremental software testing and hardware testing that Austin mentioned earlier, we came up with a flow chart visualizing our state machine for the main file. After we power on, we enter the initialization state. This state is where we start up our ADC, our controller area network modules, and get the board ready to move. We then enter our idle state. Our idle state acts as a waiting state until the driver is ready to start moving. While we're in the idle state, we retrieve information from the MPPTs and check them for errors. If we find any errors, we set an error flag and report these errors to the main CAN bus and the RS-232 port for the user to see. Assuming that no errors have been found, and we receive the 504 message, which is the message stating that the driver wishes to start driving, we move into general operation state. This is where we implement our heartbeat timer, which ticks every 5/12 of a second. At every 5/12 of a second, we execute our Coulomb counting algorithm that I mentioned earlier. After a second has passed, we get the data from the MPPTs again, and then we report our Coulomb count statistics. After 2 seconds have passed, we send that MPPT data that we got earlier out to the main CAN bus for other components to use. We do have a charging state here. However, we need information from the to-be designed battery protection system, which has not been designed yet. So we have not implemented that state, but it is a future revision. For our software development, we use Code Composer Studio by Texas Instruments. Code Composer Studio made sense as the university has a site-wide license for it, and we are using a TI MSP 430. We also use the Git revision control system to make sure that to manage our workflows and manage our code.
We then started our system integration testing, so we took our array controller and we hooked it up to the current solar car. And by doing this, we took the MPPT and we hooked it up to the solar array, which you can see on the top left. That drove current through the MPPTs, and we could start getting actual voltage readings, and we could test other functionalities like CAN and see communication from battery protection system as well.
So you can see in this animation, this is our boot up sequence. We've slowed this down considerably in order so you can see it. It moves so fast that normally people wouldn't be able to see it. However, if the spore were to get stuck in the initialization sequence, it would get stuck at one of these binary numbers here. When it gets stuck, the Sunseeker team can take a look at the number, look up the documentation, see what has gone wrong.
This slide shows the functionality of the PowerPoint trackers. There's a blue light that indicates whether it is on or off, and a CAN message is sent to the device to change its state. And through control, the driver of the car can manually control it through driver switches if needed, but it can also change states in the main program if certain conditions happen. And this slide shows the CAN. We used a CAN USB interface which was hooked up to the control area network of the vehicle. And if you can see in the picture, the timestamps with the address identifiers of 600 messages represent data from the array controller. So this is sent out to the CAN bus and it can be used from other car electronics if needed for processing.
CAN is fun and all, but RS2 is where it's at. RS232 we use to output human readable data out to the user's computer. When they send an ASCII representation of a carriage return, we tell them that the prompt is accurate. They can then send an ASCII representation of the numbers 1 through 6 to get different data readings from the array controller. When they finish, they can send an ASCII representation of a 0, and we'll tell them exactly the prompt. This is an example of some of the data that we collect in the array controller, such as the battery voltages that I mentioned earlier that we get from the MPPTs. Do know that some of these values are negative because we've designed the array controller for 3 MPPTs, but we only use 1 for testing. Had we used 3, all of these values would be positive.
If there was a next generation model of our board, there are some considerations to be made because we made a few mistakes. First off, if all you can see here, that connector is supposed to be on the top, as you can see in the picture on the right. However, we designed it accidentally to be placed on the bottom. Luckily, it wasn't a big mistake and we were able to continue. Also, I'm not sure if you guys can see, but this connector hangs off the board right here, this little one. And it's supposed to be, it is right angle, but it's supposed to be on the board, but we accidentally designed it for vertical. So luckily it didn't halt our project. And then also we would add MPPT CAN voltage and resistive reference.
As far as recommendations go, one recommendation we had was to have software be testing concurrently with hardware development to increase productivity. Another thing that we would recommend is have a more streamlined purchase of parts because we sent out 3 or 4 separate DigiKey orders and that cost more time, more expensive in shipping. And we would also recommend looking into getting more freebies so you can save on your expenses on your project. And none of us were members of Sunseeker, and as we struggled initially to have the big picture of all the hardware work together. And it's hard to design a subsystem without fully understanding the full system. And as John previously stated about the mechanical considerations, the footprints, I'd recommend that we fix those. And for the next generation PCB, I'd recommend also a more compact layout because the first gen, we were more concerned about functionality and not necessarily compactness.
We want to thank you all for coming out to our presentation today. We want to thank our families for your support. Sunseeker team members, especially Robert Gullman and Brian Harris, they helped us with our system testing and integration. And also our advisor, Dr. Bazine, for helping us throughout the whole project and guiding us.
Any questions?
What's the percentage load that your electronics put on the Sunseeker system? You know, including the shunt and the electronics.
The load?
Yeah, what percentage? You take some energy to run your electronics.
Oh,
what does that represent?
Our board runs on less than 2 watts.
And the overall power for the Sunseeker is about?
I think it's about over a kilowatt. Right? I'm not really sure.
It's not taxing the system.
I have a couple of questions. One of them was the long counter we have. This is a dumb question, but like the battery charges, it also discharges. So the coulombs that's left is the difference between both ends or something?
Yes,
Okay. We figure out that difference by doing the battery protection system, which is to be designed with a current the senior design 1 class has a group that will be designing. They're actually right there. So we don't, our board currently does not know how much is leaving, we know how much is entering. Once that new battery protection system is built, we're able to know how much is leaving and how much is entering, and then we can make our decision to enable or disable it.
And one other question. You mentioned about complexity, but would you be more specific? So we should handle complexity. Would you say what hitch you ran into?
Oh, well, the way school goes along is you don't really get into considerations of the mechanical connectors. That was this power right here, this MPT can, this can's a mistake. So that was new to us, is how to deal with real world connectors. And another issue we had was isolation. I've never seen a reason for isolation until this project. And then another thing that was complicated is a lot of the circuitry. I've never done any of this PCB layout before. We had to learn the software. We had to learn how RS-232 worked before we had lab in one of our courses, and that was Joel's doing. So it was a lot at once, and we had to learn on the fly.
How much did the whole project cost?
Yeah.
Dr. Design bought the boards. They were about $750 for 6 of them, because we have one on display right now, but he wanted a spare in case during race conditions something happened. We had a backup instead of wasting time to debug. You just throw it in. And then the parts cost, I think we spend
Way too much.
like $200 a piece on parts, maybe.
What happened is we had a lot of panics where we were like, oh my god, we don't have this, so we'd buy like overnight shipping, like $60 or $70.
Which goes into the recommendations of making one single purchase order to
Yeah.
save on money. We spent in shipping costs 3 or 4 separate times.
Yeah.
So it was roughly about $1,100, $1,200.
Yep.
So, in real world designs, you'll find out that maybe 88% of the time is spent debugging and so forth. So how much time did you spend designing versus trying to get it to work?
Probably
Debugging hardware.
We spent most of last semester from October till about December designing, and then we spent roughly a month and a half working on layout, and then we spent roughly 2 weeks assembling the boards with the spare. We actually made a mistake. I put a part upside down, and we had to take it off, and the pads got pulled, so that component wasn't going to be used. We had to reuse a different board. The good thing we had spares. And then individual software testing took maybe
About a week and a half.
About a week and a half.
That's bad.
And then system integration, we spent 2 weeks maybe.
Yeah, about 2 weeks.
So we front load our design, and then the testing went fairly smooth.
Luckily, it went fairly smooth.
Thanks to the Sunseeker team.
Yeah.
Our software was provided to us from Dr. Design. We used past Sunseeker code, and we had to modify it for our project and everything, so there wasn't a lot of changes, but, so. We had to write our own, for the CAN, we had to write the remote transmit requests, functions and everything, but it didn't take too long. We just referenced data sheets and, project.